Okay, let's start the class. So good morning. So today we are going to talk about proof by contradiction. And then, okay, so what is this? So before we talk about this, we will talk about, so I hope you still remember something about this logic. So suppose that P is a statement which has a true or false as its value. Q is another statement which has true or false as its value. So these two are propositions. Then, from logic, we know that P implies Q, this new proposition or this compound proposition, is always having the same truth value as not Q implies not P. So for instance, okay, so let's say this one. So let's say P represents I have buffet dinner. And then let's say Q represents I'm full. Okay. And it turns out that, okay, if I have buffet dinner, then I will be full. This is going to be true, right? So let's take a look of what is the opposite. Okay, so by common sense, this is going to be correct. If I have buffet dinner, I will be full. Then this one, not Q implies not P, it will say, if I am not full, then I do not have buffet dinner, which is also correct, right? This is common sense, okay? So in general, for any proposition P, any proposition Q, P implies Q is always having the same value as not Q implies not P. They agree in the truth value in any cases. So we will say that these two, this proposition and this whole proposition, they are equivalent. Okay. So sometimes in some mathematical statement, we want to show that P implies Q is true. We want to show something is true. But this somehow could be difficult. So instead, we may also show the alternative statement. We want to show that not Q implies not P is true. Then this will have the same effect. So using a proof in this way, we call it an indirect proof. We are not proving the original statement directly. We are showing indirect proof. So there are two main types of indirect proof. This is one case. P implies Q. We do not show this directly. We show not Q implies not P. This is called proof by contraposition. And then today we will talk about a special case of this proof by contraposition called proof by contradiction. So what we are going to do? So again, suppose that we have a statement P. Is that okay? Okay. And then let's say there is something called always true. So let's say T represents something always true. Then if you look at this case, T implies P will be a new proposition. But you see that if P is true, then T implies P will be true. If P is false, T implies P will be false. Am I correct? So in that case, these two things is actually equivalent. Okay? Okay, so it doesn't make sense to say that if I want to prove P, then I want to prove T implies P, because it's actually the same thing. But look at what happens if we look at the contraposition of this one. So this is of the form something implies something. So this will be equivalent to what? This will be equivalent to not P implies not true. So not true, actually, we will use F to represent it, false. Okay, so that means that P and not P implies F will be equivalent in all the cases. So if I want to show P is always true, P is a theorem that is always correct, then it is the same as if we are trying to show that not P will imply false in all the cases. So this is, rather than proving P directly, we prove not P implies F. And this technique is called proof by contradiction. Okay? So why do we call it contradiction? Because the F itself is called contradiction. Something that is always false is called a contradiction. And something that is always true is called a tautology. Is that okay? So this is the idea. So the proof strategy is, if I want to, so we are going to look at a few examples today. So let's start with an example and see how we can apply this strategy. So let's say the first thing that we want to show is, so let me define. So a number x is called rational if x can be expressed as p over q, where p, q are, they are integer, and then q is not equal to 0. Is that okay? So this is called rational. So otherwise, the number x is called irrational. Is that okay? So this is the definition of a rational number. And then we are going to look at this theorem. Let me try this. So we're going to look at this theorem. The number square root 2 is not rational. It is irrational. Okay? So we want to show this one. Now, a direct proof turns out to be super hard. So you want to show square root 2 is rational directly, you need to check what? You need to check all possible p and q, integer p and q, with this form, and then they are all not equal to square root 2. So there are going to be infinite number of cases, and then we will not be able to solve this. And then induction, well, there is an induction proof of this one. We will make it as an exercise perhaps, but let's try to show it by contradiction. So to prove this, by contradiction turns out to be quite easy, okay? So in order to show this is correct, the whole thing, so what we are going to do, we want to get not p, and then hope to get a contradiction, something that is always false in the end as the conclusion. Then we prove this. So perhaps we can write down something like this. The proof strategy, we write down it is by contradiction, so that people know you are going to use contradiction and won't get lost of what you are doing. So here, so what do we assume? So we assume, to the contrary, of the theorem that square root 2 is rational. Okay, so we are trying to assume not p at the beginning, and then hope that after some statement, we can get a conclusion that is always false. Okay, so assume contrary that square root 2 is rational. So square root 2, you can write it down as p over q for some integer pq with q not equal to 0. Is that okay? Good. Let's continue the proof. Okay. Since square root 2 is positive, so we may assume that p and q are both positive integers. Is that okay? Further, assume that p and q are both greater than 0. Is that okay? Also, So without loss of generality, we can assume that the greatest common divisor between P and Q is equal to 1. So PQ do not have any common factor. So why can we have this assumption? Why? So this one makes sense, right? So we are trying to say that square root 2, you can express, if it can be expressed as P over Q, then we can first assume PQ are both positive because the other case is PQ are both negative. We multiply them by -1 each. So we get positive P and positive Q. Now, this is a strange thing. I'm saying that without loss of generality, so we can generally choose PQ, but it's also okay that we make a further restriction that PQ do not have any common factor. The greatest common divisor is equal to 1. Why? Why can we make this assumption? Why I can make this assumption? So why? So for instance, if PQ do not have, let's say PQ has some common divisor, 5. Let's say P is equal to 100. Let's say Q is equal to 75. So there is a common divisor of 5, right? Then what can we do? So we can divide them by 5, right? So we get 20 and 15. Am I correct? And then there is still a common factor, right? So we can still divide the common factor. So we will be able to divide them by the largest common factor, okay, greatest common divisor actually, on both P and Q, so that we remain the same ratio, but then the new P and the new Q will not have any common factor. Does that make sense? Okay, so of course, if you need a proof, make sure. So if you are presenting this for someone who is not familiar with what we can do, so we better tell the reason. Otherwise, we divide GCD of PQ on P and Q and get the new P and the new Q, something like this. Okay, good. So what do we have? So now, this is going to be a key thing that we will rely on. So let me make a mark here. So next, what we can do, so then what do we have? Then, because square root 2 is equal to P over Q, so we will have 2 is equal to P square over Q square, or 2Q square is equal to P square. Is that okay? So this will imply P is even, because this is even. So P cannot be odd. Odd times odd is equal to odd. So P must be even. Does that make sense? Good. So, okay, so we let P is equal to 2 times some R, where R is an integer. It's an integer, let's say any integer. Okay? So P is equal to 2R. R is an integer. Then what do we have? Then, so we can plug that in back. So we will have 2Q square is equal to 2R square, right? So it is equal to 4R square. Okay. So 2Q square is equal to 4R square. So Q square is equal to 2R square. And this again implies Q is even. Reason. Okay, so the reason is the same because 2r squared is even. Q cannot be odd. Odd times odd is odd. So it must be even. Now we get a contradiction. Now a contradiction occurs. Where is it? Where is it? So suddenly a contradiction occurs. So where is the contradiction? First of all, under the assumption that square root 2 is rational, then we can get P and Q. And then we can get P and Q without any common factor. And then we get P, which is even, and then we get Q, which is even. So we get PQ has common factor 2. Okay? So the contradiction comes from P and Q does not have common factor, and P and Q has common factor. Is that okay? So we get two things. One is of the form a sentence, some sentence W, and then the other is of the form some sentence not W, under the same assumption. So under the assumption that not P is correct, the square root 2 is rational, under this assumption, then we get the statement W. We get another statement not W under the same assumption. Okay? So W and not W are both consequence of our assumption. So W is true, we are claiming, and we are also claiming not W is also true. So W and not W is also true. So that means that we get something like W and not W, which is a contradiction. So a contradiction occurs. So you want to explain what is the contradiction. If you are uncertain whether the reader of your proof understand what you are talking about. So the contradiction comes from PQ does not have common factor and the fact that PQ now has common factor. Okay? So you can end the proof like this. But to make the proof looks more complete, so the assumption is not correct, it's false. So the theorem will be correct. So the theorem follows. Okay, is that okay? So at this moment, we have a contradiction. So we finish the contradiction proof. So we will conclude that the original assumption that we made is wrong. So the opposite of this assumption must be correct. So the theorem will be correct. Is that okay? If you're okay with this proof, could you please raise your hand? Okay, good. Good. Okay, let's try another one. Okay, let's try another one. So how about this one? Okay. So let's do another theorem. So this theorem says there are infinitely many prime numbers. Okay, so 2, 3, 5, 7, 11, they are primes, okay, because they have just itself and 1 as the only divisor. And then for a long time, people ask, will we run out of primes? So after 2, we get 3. After 3, we get 5, right? After 11, you still have 13. But it is actually, you will never run out of primes, because there are going to be infinitely many primes. Now, if you look at this theorem, again, the direct proof is impossible, unless you have a general formula that you can produce the next prime, or you can produce some prime that is at least one prime that is greater than a specified number. Okay, some people try to do that, but then still not successful. Okay, but to prove this in the opposite way to prove this by contradiction becomes easy. Okay? So let's take a look of how do we prove this. So again, we write down by contradiction. So we assume what? Assume to the contrary. That there are a finite number of primes. Of primes. Is that okay? So we have finite number of primes. Make it n u. Okay. So because there are finite number of primes, we can list them out one by one. Let us call them P1, P2, up to Pk. And that's it. They're just k primes. There's nothing else. Okay? Now, let us consider a new number. The number, this number is q, and then it is equal to, let's try to multiply all of these primes together. We multiply them together, and then plus 1. Okay, now, very interesting. This q is a super large number, but one thing that is interesting is that this is the interesting thing. Q is not divisible by any pi. None of these primes that we know, we have listed them out all, but none of these primes can divide Q. Because if Q is a multiple of, let's say, P1, then this is a multiple of P1. This is a multiple of P1. So if we minus this thing on the left-hand side, we still get a multiple of P1, right? But then 1 cannot be a multiple of P1. P1 is greater than 1. Any prime number is greater than 1. So 1 cannot be a multiple of P1. So in that sense, P1 cannot divide Q. P2 also cannot divide Q. So none of the primes that we know divide Q. What does that mean? Either we have missed some prime factors of Q. We didn't list them out, but we say list them out. Oh, okay. Or Q is a prime by itself. But then again, Q must be greater than this Pk, right? We are multiplying everything, and then plus 1. So this will be greater than this one. So in either case, we get a contradiction. So what is the contradiction? Contradiction is we list out all the primes here, but then here we are missing some primes. So all the primes are P1 up to Pk. And here it says that P1 and Pk, P1 up to Pk are not all the primes. So we get a contradiction at this point. So writing out what I'm just saying, then you get a contradiction. So you get something wrong. There is a contradiction. So once we have a contradiction, then we will know that so a contradiction can only occur when we are making a wrong assumption at the beginning. So that means that the assumption at the beginning is wrong. So if this assumption is wrong, then the opposite of this assumption will be correct. Okay? So that means that the theorem will be correct. Is that okay? Okay? If you're okay with this, could you please raise your hand? Okay, good. Good.